In this video, we review the Maxwell distribution of speeds. This video follows naturally from our understanding of kinetic theory of gases, where we have introduced the concept of the average kinetic energy and the root mean square speed. What those concepts tell you is that when you think about a gas, like the one that I'm breathing in right now, the speeds of those gas particles is not always the same for each particle. Instead, some particles are moving fast, some particles are moving more slowly, and you have a distribution of speeds. Right? So it turns out that a scientist called Maxwell worked out how the distribution of speeds looks like, and that's what we have right here. Okay, and what we have is that there's two parameters to this equation, to this distribution of speeds, and one of them is the molar mass, right? So how fast the gas moves depends on how heavy it is. And then also on temperature, okay, and both of them are there and here, right? So we also know that when a gas is hotter, then on average those gas particles are moving faster. Right, so we're going to try to draw this probability distribution, then see how the parameters affect the distribution, and then we'll see what are other things that we can learn from that concept of the Maxwell distribution of speeds. Okay, so first of all, we're going to try to plot this distribution. Now, notice that if you set on a gas like argon or CO2, then the molar mass is set, and if you set on a temperature, say 300 Kelvin, then the temperature is also set. So really the only variables that you have is the velocity, right? So notice that what you have here is a product of two functions that depend on velocity. This one, which is a quadratic function, and this, which is a Gaussian function centered at zero. So the products of those two is what is going to be the probability distribution. All right, so let's try to see if we can draw that. Okay, so that will be your probability distribution versus speed. And then again, we have the product of a quadratic function, which would look like this, and a Gaussian function centered at zero, which would look like that. Right? It's a bell-shaped curve where you're only looking at the positive part of that curve. So the product of those two looks like this. All right, where you have that this curve slowly goes all the way to zero as velocity approaches infinity. Now, let's try to study how the parameters of this equation affect the shape of the function. Right, so again, you have two parameters, the molar mass of the gas and then the temperature of the gas. Let's try to see the molar mass first and see what those terms are. Notice that the molar mass enters the equation in two different places. One here, and then another one there, okay, up here. And it turns out that the exponential dependence is much stronger than this dependence that you have right here, which is the 1/2 root of the molar mass. The exponential dependence is much greater. Okay, so let's actually see the trends. You can simply just think about how changing the mass affects that part of the distribution, and that will be actually very useful for you to, again, anticipate what the trend should be. All right, so let's suppose that we are making this gas lighter. Okay, so this is a mass m sub 1, and then this mass is going to be greater than the mass m sub 2 and a mass m sub 3. Right, so for a lighter gas, what that means is that this mass becomes a little bit smaller. Okay, so what you have here is an exponential to a negative number that it becomes increasingly smaller. What that does is that flattens out that tail of the exponential distribution towards higher velocities, right? So in effect, what that does is for M2, it actually makes the curve go like that. Okay, so it would be, this is for M1, this is for M2, and if you decrease the mass even more, then you're taking the exponential of a negative number is going to be increasingly smaller, and again that flattens and extends that distribution towards higher velocities even more, right? So you will have something that looks like this, and then so forth, right? So that would be m sub 3. All right, so this makes perfect sense, right? So let's think about this in terms of actual gases. For example, rare gases. Compare xenon, which is a massive gas, to maybe argon, which is intermediate, and helium, which is very light, right? So the helium gas, if they are the same temperature, so the temperature has to be constant, in order to make this comparison legit, let's assume that this is 300 Kelvin. Right, so if they're all at the same temperature, notice that the average kinetic energy of each one of them will be exactly the same. However, helium is much lighter than xenon, so that means that in order for helium to have exactly the same average kinetic energy as xenon, then helium has to move much faster, right? So that's what the speed distribution would be, right? Notice that on average, those helium atoms are moving really much faster than these xenon atoms, right? All right, so that's the dependence on the molar mass. Let's now examine what the dependence on the temperature would be. All right, so what we then do is now fix the molar mass to whatever value we want, and maybe we can do this, we can make this be m equal to argon, just for example, and then we're going to be changing the temperature. Okay, so now we're going to examine what the variation with temperature would be. All right, and we can start to see how that temperature effect plays in by looking at the exponential term again. You have a temperature dependence here, but that is going to be much more subdued than the temperature dependence that you have inside the exponential. Right, notice that you have now the temperature dividing in that exponent, right? So when you make that temperature low, what that means is that you're taking the exponential of a negative number that is high, and that means that this curve will actually be compressed towards lower velocities, right? So what we have here is that in this case, that will be the lowest temperature, T1. If you increase the temperature, then the curve displaces to larger average velocities, the curve flattens out, and again you extend to much larger velocities. Let's try to make sure that this makes intuitive sense, right? So now consider a simple gas like argon, and then think about that gas at 100 Kelvin, 500 Kelvin, and 1000 Kelvin. Okay, so well, what we know is that the average kinetic energy should increase, right? Because it depends on the temperature linearly. That means that on average, those particles are going to be moving much faster as you increase the temperature. Okay, and that's exactly what happens, right? So this will be your largest temperature, 1000 Kelvin. Those molecules are moving on average much faster than at 500 Kelvin than at 100 Kelvin. Okay, so that is how this Maxwell distribution of speeds depends parametrically on molar mass and temperature. We're going to wrap up this video by again taking a look at what other type of information you can get from this speed distribution. Okay, so let me erase these trends here and just draw a general curve to explain this probability distribution. All right, so here is a generic probability distribution, and now the questions that we're going to be asking in problems would be, well, what is the peak speed, right? How do we actually calculate the velocity at which you have that peak speed? This is called the most probable speed. Okay, so well, what you actually know then is that at this point, the first derivative of the function with respect to the variable is 0, because the slope of the line tangent to that line is 0. So a way to find this most probable speed would be to take the first derivative of this with respect to the velocity and then make that 0 to solve for the velocity. And there will be a problem in the homework. A different set of problems in the homework engage the idea that this distribution is a probability distribution. Okay, and what that means is the following. You can calculate the probability that a set of particles have a speed in a given range by simply taking the integral of the function with respect to the variable in that range, right? So the probability of having particles between v1 and v2 will be the integral between v1 and v2 of the function, and the variable is this velocity. All right, so this looks like it's really complicated, but it actually really isn't, right? So again, the idea here is that we might ask the question, well, suppose that I want to know how many of my argon particles or CO2 or whatever gas this is have velocities between, oh, I don't know, 795 meters per second and 805 meters per second. Well, what you would actually have to do is take the area under that curve. right? That's one of the characteristics of probability distribution. The area under the curve give you the probability. Okay, so, well, this looks quite complicated because, again, notice that here you have to take the integral of something that is pretty tough, right? But it turns out that if the interval that you're looking at is very narrow, then there is an approximation that you can invoke that is extremely useful. Okay, so notice that what I'm going to do is now blow up this range right here, okay, and see what is the approximation that we can take. Right, so the function looks like this, okay, and notice that we have to take that integral right here, so measure this area. Well, one of the things that we can actually do is that if the range is very narrow, we can assume that that is a straight line. That function is a straight line, and that only works well if the range is narrow. But if this is a straight line, then what we can do is simply calculate the midpoint of the interval and then just make the curve be like that, right? Notice that if that is a straight line, then what you're actually doing is the area in this rectangle is exactly the same as the area under that curve, and that works really well. Okay, so notice that mathematically what that means is that you're considering that the function is constant, so then you can factor it out of the integral, so then your probability is simply the evaluation of the function times the integral of differential of v, which is just a change in temperature, in velocity in the range, right? So that would be 805 meters per second minus 795 meters per second. And again, you will see how this plays out in a homework problem. Okay, so with this we wrap up the discussion of Maxwell distribution of speeds, in which we have learned what is the function that characterizes the speeds with which gases are moving for a particular molar mass and at a given temperature. We have also learned that that distribution of speeds is a probability distribution, so you can actually calculate the probability that a given fraction of particles have a speed in a range, and we will learn how to do that in the homework problems.